Alright, in this video we're going to take a look at an introduction to organic functional groups in the Advanced Chemistry Organic Chemistry unit. A functional group is just a group of atoms within the molecule, within an organic molecule, that is responsible for the characteristic chemical and physical properties of that molecule. We organize organic molecules, the huge variety of them, by these functional groups. For example, we're not going to look at it here, but we know that when you see a hydrocarbon with just single bonds between carbons saturated with hydrogen atoms, we know that that's called an alkane. If you see double bond within a double bond within the hydrocarbon, then we'd call that an alkene. So you can think of the double bond as being the alkene functional group. You can think of a triple bond as being the alkyne functional group. What we're going to look at here are some other ones that you might have come across in a biology course, in a biochemistry unit, because they're pretty common there. The first one, we're not going to go into much depth on, but it's organic halides. Remember that halogens are the group on the periodic table. Fluorine, chlorine, bromine, and iodine are the common halogens. And so if you see a hydrogen removed from an alkane or an alkene or an alkyne, and it's been replaced with a chlorine or a bromine or a fluorine, etc., you now have an organic halide. The nomenclature of that kind of thing is pretty straightforward. I'll draw a bond line formula of one here. So if you have, let's say, propane, so 3 carbons, propane, and let's put a chlorine atom on the first carbon in the chain, and let's put a fluorine atom on the second carbon in that chain. So now we know we have an organic halide. To name it, we would say that, well, 3 carbons, 1, 2, 3, that's a propane molecule. We'd start numbering at the end closest to the first branch, so this would be carbon 1, carbon 2, carbon 3, and then we would name the branches alphabetically. So chlorine would come before fluorine, so this would be 1 chloro dash 2 fluoro, and then 3 carbons propane. Right, so chlorine becomes chloro, fluorine becomes fluoro, iodine would become iodo, etc. All right, so naming organic halides is a pretty straightforward exercise. It's very similar to naming branched alkanes. The second type of functional group is now one that's a little bit more important. It's called an alcohol. Alcohols are characterized by what's called the hydroxyl group. The hydroxyl group. The hydroxyl group is an OH, so it's an oxygen-hydrogen attached somewhere to your hydrocarbon chain. Now in these generic formulas with functional groups, the letter R simply means the rest of the molecule. Usually, but not always, but usually it'll be some kind of carbon chain, some kind of alkyl group. If there's an R with a prime symbol beside it, that's simply saying that the 2 R groups, the 2 alkyl chains, don't have to be identical. For example, here we could have a methyl group, and then we could have another methyl group, or we could put an ethyl group there, or a propyl group. So to distinguish them, sometimes it's just an R, sometimes it's an R prime. So an alcohol has an R group, so some kind of carbon chain, with an OH attached. Now when most introductory chemistry students see OH, they think of the hydroxide ion. Remember, this, though, is not an ion because we're dealing with a covalent compound. We're dealing with a molecular compound. Only nonmetals are present. So there's no ions. So instead, this hydroxyl group is covalently bonded to a carbon atom within the molecule. All right, I'll show you a few alcohols, a couple of them. Here's a very common alcohol. Okay, this is the type of alcohol that you'd be familiar with if you drink beer or wine or something like that. It's called ethanol. It gets its name ethanol because it has 2 carbons. So 2 carbons in a hydrocarbon we know is called ethane. And then we see the hydroxyl group, OH, attached to one of the carbons. So this tells us we're dealing with an alcohol. To name the alcohol, we simply take the name of the hydrocarbon, in this case ethane, and we would drop the E and we would add OL. So ethanol is the name. All right, now in the case of ethanol, there's only one carbon that that alcohol group could have been attached to. Here I've attached it to the left-hand carbon, so that's the first carbon in the chain. Notice if I had attached it to the second carbon, it would be the same molecule, just flipped over. So we don't need to number the carbon that has the alcohol attached to it, that has the hydroxyl group attached to it. On the other hand, if you look at a slightly larger alcohol, so here is an alcohol with 3 carbons. Okay, you can see the propane, we remember, is an alkane with 3 carbons in it. And here's the hydroxyl group that identifies this as an alcohol. Now in this case, the hydroxyl group is bonded to the second carbon in this 3-carbon chain. It could have also been bonded to either this one or this one, in which case it would have been bonded to the first carbon in the chain. So now it becomes important to say exactly where in the molecule the hydroxyl group is attached. So in this particular example, with the hydroxyl on the second carbon in the chain, we're going to start thinking about propane, a 3-carbon alkane, and then we'll drop the E and we'll add an OL. Now in the UPAC system of naming, you would say propane-2-all. And that 2 is telling us that the hydroxyl group is on the second carbon in the chain. In your Zumdahl textbook or on WebAssign, the American tradition is to put the 2 in front and just say 2-propanol. Okay? Now this molecule has an older name. This particular arrangement of carbons, when you have a 3-carbon chain attached by this center carbon to something, it was often called isopropyl. So this can also be called isopropyl alcohol. It even has another name. You could call it 2-propyl alcohol. There are many, many different names for organic molecules. We're going to generally follow the UPAC, the International Union of Pure and Applied Chemistry, the UPAC system of naming, and we're going to try to follow the system that says propane-2-all on my tests and exams. So those are alcohols with the hydroxyl groups in them. The next type of functional group on this chart is called an ether. Okay, ethers. And ethers are identified by having an oxygen atom with 2 R groups attached, and those R groups cannot be hydrogen atoms. So these have to be alkyl groups. They may or may not be the same alkyl groups. So let's take a look at one of the simpler ethers. Got one prepared for us here. This is the simplest possible ether. Okay, so you can see it's got a methyl group bonded to oxygen, bonded to another methyl group. So there's 2 methyl groups, this would be R and R prime, bonded to oxygen in the middle. So this is an ether. Now there's a couple of systems for naming ethers. We're going to follow a UPAC system that's a little bit it's reserved mainly for simpler ethers, and that's all really we're going to look at. So what we're going to do in this ether is we're going to name one R group, then the second R group, and then we're going to say ether at the end. And if the R groups are different, we name them alphabetically. So in this case, we have 2 identical R groups, 2 methyl branches. So you might say methyl-methyl ether, but usually we would just say dimethyl ether. Okay, 2 words, dimethyl ether. If the R groups were different, here we've got another ether, slightly larger molecule. You can tell, I hope, that it's an ether because it has an R group here, a methyl branch, and another R group here, an ethyl branch, and there's an oxygen joining them, so that's an ether. Now this has a methyl and an ethyl, so we're going to name them alphabetically. and we would say ethyl, methyl, ether. Right? Ethyl, methyl, ether would be the name of that ether there. All right, the next functional group. Now, I'm only introducing these things, right? They get more complicated. You can have branched molecules as well, but since you already know how to name branched alkanes and alkenes, I'm pretty sure you'll be able to just transfer that knowledge to these slightly more complicated molecules. So next I'm going to take a look at aldehydes and ketones because they're related. Aldehydes and ketones are characterized by what's called the carbonyl, or the carbonyl is how I usually pronounce it, the carbonyl group. And it's a carbon atom with a double bond to oxygen and then two other R groups attached. Now, in this case, if one of the R groups is hydrogen, at least one, you would have the carbonyl on a terminal carbon in the chain. For example, if we look at a longer carbon chain, if I put this C double bond O at the end of the chain, or of course I could have put it on the carbon on the left, that would also be at the end of the chain. So if I do one of those two things, I have a carbonyl terminal at the end of a chain, and this carbon here must have a hydrogen attached as well, right? So this is the characteristic structure of an aldehyde. Aldehydes have the carbonyl group with a hydrogen attached, at least one, because it has to be a terminal carbon with the carbonyl, and then an R group attached as well. So the simplest possible aldehyde is a single carbon. So it's got a carbon with a double bond to oxygen, and then here's the hydrogen. And because it's just a single carbon, there's one other hydrogen also attached. So this would just be CH2O. So with one carbon, you'd think of methane. Okay, let's put that back there so you can see it again. So methane has one carbon alkane. We drop the E from the ending of the name methane, and we add, remember we're naming an aldehyde, so we call this methanal. AL at the end. So methanal. Here's a slightly larger aldehyde. Okay, this one here has 4 carbons in a chain, and there at the end of the chain is the double bond oxygen, so there's the carbonyl group, and again it's on a terminal carbon, it's on the end carbon in the chain. So this is what characterizes it as an aldehyde. So 4 carbons, we would think butane is a 4-carbon alkane, so butane would be how I'd start in thinking about that. I'd drop the E from the ending of butane, and I'd add the AL suffix. So butanal is the name of a 4-carbon aldehyde. Okay, and again, if it were branched, it would be a little bit more complicated name, but the basic name, the parent portion of the name, would still be butanal. If it were branched in any of these cases, you would start numbering the parent chain at the end of the chain closest to the functional group. So for example, if we had a methyl branch on this carbon here, we would start numbering the butane chain over at this end, because this is where the aldehyde is attached, the carbonyl. So this is carbon 1, carbon 2, carbon 3. If there were a methyl attached to this carbon, we would say 3-methyl butanal. All right, so remember to start numbering the parent chain in a branched molecule, always at the end closest to the functional group. The functional group takes priority over any branches. All right, a close relative to aldehydes are ketones. Ketones, you'll notice, also have this carbonyl group. They have a C double bond O. The difference, though, between a ketone and an aldehyde is that the carbonyl group for a ketone is not terminal. So it's not at the end of a chain, which means the two R groups in a ketone will never be hydrogens. Okay, these cannot be hydrogens, otherwise you'd have an aldehyde. So the simplest possible ketone would be this one. We have a 3-carbon chain, and we've got the carbonyl group, the C double bonded O, on the center carbon in the chain. So the two R groups here are both methyl groups. So now, how do we name a ketone? So what you do is you start again with propane, would be the name of a 3-carbon hydrocarbon, and you drop the E from the ending, and ketone, this time we're going to focus on the ending of the name of the functional group, we would call this propanone. Propanone. Okay, so that shouldn't be there. Now some might say that this is 2-propanone or propane 2-one, but I don't think that 2 is actually necessary in this molecule, because if you say propanone, then you've told me it has 3 carbons, propane. You've told me propanone, that it's a ketone, which means the carbonyl group can't be at the terminal carbons. That left only one possible carbon where the carbonyl could be. So propanone is a sufficient name. You don't need to say propane 2-one. But if the carbon chain were longer, okay, so here's a longer carbon chain. This one has 5 carbons, right? So 1, 2, 3, 4, 5 carbons. Now, if I say pentanone, notice that that's not a sufficient name, because you wouldn't know in the name pentanone whether or not the carbonyl group was on the 2nd carbon, as it's shown here, or on the 3rd carbon, right? There's 2 possible places to put the carbonyl group. If you put it on the 2nd carbon, you'd have 2-pentanone using the American system, or pentane 2-one using the UPAC system. If you put it here on the 3rd carbon, you'd have 3-pentanone, or pentane 3-one. Notice if you put it over here, you wouldn't have 4-pentanone, because you'd have to start counting the carbon chain at this end. You'd have 2-pentanone again. So always start counting the parent chain at the end closest to the functional group. So this particular molecule's name, we'd start with pentane again, 5 carbons. We drop the E and we add -one because it's a ketone. And here it's on the 2nd carbon, so I'm going to say pentane -2-one. And again, the American system would be 2-pentanone instead. All right, so ketones and aldehydes are related because they both have carbonyl groups. The difference is that in an aldehyde, the carbonyl's terminal, it's at the end of a carbon chain, while in a ketone, the aldehyde is somewhere in the middle of the carbon chain. Next, we'll take a look at carboxylic acids. A carboxylic acid is characterized by the carboxyl group. Okay, the carboxyl group. The carboxyl group is this carbon with a double bond to oxygen and then an OH also. And you might be tempted to think of this as a carbonyl group with an alcohol group also, and I understand why you'd think that, but try to avoid that because it behaves in a totally different way. This is an acid. When you put the carboxylic acid in water, this hydrogen atom attached to the oxygen dissociates and results in a lowering of pH in the solution. So carboxylic acids are characterized by this C double bond O OH. The simplest carboxylic acid would have a hydrogen attached over here where there's an R group, and then we'd have what's called methanoic acid. The second simplest carboxylic acid would be this one. Okay, it's got 2 carbons and then the double bond oxygen and OH. Okay, so 2 carbons double bond oxygen OH. This COOH is what characterizes it as a carboxylic acid. So I would start by saying ethane, because there's 2 carbons in there, and drop the E from the name ethane and add oic acid. So ethanoic acid. Now, ethanoic acid has a much more common, older name that's still used today. Ethanoic acid is called acetic acid also, and of course that's the acid that's found in vinegar. Now if you remove that hydrogen from the OH, remember I said that it dissociates in water, what you'd have now is CH3COO minus, and this would be called, in the older naming system, acetate, the acetate ion. In the newer system, this would be called the ethanoate ion. Okay, the ethanoate ion is an ethanoic acid molecule after its hydrogen bonded to that oxygen, OH, dissociates. So you get ethanoate ion, which is a complex ion. Okay? A slightly larger carboxylic acid. Okay, this one here, you can see has 4 carbons, 1, 2, 3, 4, and the last carbon is what characterizes as a carboxylic acid, C, double bond to oxygen, and then OH. So COOH is what jumps out at me as a carboxylic acid. Now, how would you draw that with a bond line formula? Well, 4 carbons, 1, 2, 3, 4, and then double bond OH. Okay, so there's the characteristic way to draw it using the bond line formulas. So 4 carbons, we're thinking butane, and then we drop the E and we add oic acid, the butanoic acid molecule. If this hydrogen were to dissociate and you're left with the ion with a minus charge on the oxygen now, you'd have what's called butanoate ion, okay, just like ethanoate ion. All right, we're getting near the end. Let's take a look at esters next. An ester, I'm going to look at it in a slightly different way. An ester is the product of a chemical reaction between a carboxylic acid and an alcohol. So let me find an alcohol. So here was an alcohol we looked at earlier. This was ethanol, 2 carbons with the hydroxyl group, ethanol. And let me grab a carboxylic acid that we just looked at. Oh, maybe about the larger one. Here we go. So we've got butanoic acid. So we've got these 2 molecules, and we're going to let them react chemically. Now, when they react, let's take a look at what happens. The H from the alcohol comes off in a collision between the 2 molecules. So that H comes off. And in the collision, the OH from the carboxylic acid also comes off. Boom. And those 2 pieces, the H and the OH, combine, and they give us a water molecule. So during the collision between these 2 molecules, water is produced, but that's a minor product. We're not interested in it. Now notice the carbon that used to have C double bond OOH now needs something to bond to it. The oxygen in the alcohol, which used to have OH, also needs something to bond with it. So you can predict now what's going to happen. The oxygen from the alcohol and the carbon from the carboxyl group, they bond, and you get now what's called an ester. Now, I'll try to fold that so in a way that you can see most of the molecule in the picture here. Maybe I'll just zoom out briefly so you can see it a little bit better. So there's the ester. Now, if you look at it, you can look at it in an intelligent way. We can see that over here we have a 4-carbon chain, 1, 2, 3, 4, which ends in something that kind of looks like a carboxyl group, C double bond O with an O attached. So it starts to look like a carboxyl group. But the O, instead of having OH, like a carboxylic acid, has O and then another alkyl group. All right, so let's look at that one more time. We see a 4-carbon chain with a C double bond O, O. So we're thinking this might be a carboxylic acid with maybe butanoic acid, 4 carbons. But instead of OH, we see OR. We see the oxygen is here bonded to an ethyl group. It's got 2 carbons in it. So that's what tells us this is not a carboxylic acid, but is instead an ester. So an ester has at its heart something that looks sort of like a carboxyl group, C double bond O with another O attached, but instead of the OH that was in a carboxylic acid, we have OR prime. And over here we have another R group. These two R groups that have to be alkyl groups, or at least this one does. This R group could have been a hydrogen atom, but the R group attached to oxygen here has to be an alkyl group. It has to have carbons in it. And so what we get is called an ester. Now, how do you name an ester? What we're going to do is name it in 2 pieces, and we're going to name first this piece, which came from the alcohol in the reaction, and then we're going to name this piece, which came from the carboxylic acid in the reaction. So in this particular example, we're going to name this piece first, the piece that's bonded to the oxygen here, and then we're going to name this piece here, which came from the carboxylic acid. So again, in the reaction, we used ethanol, and we used butanoic acid. So the ethanol produced this portion of the ester molecule, and the butanoic acid produced this larger piece over here. So to name it, we name this portion first, and we 2 carbons. We're going to say ethyl. And then we're going to name the rest of the molecule, which had 4 carbons. But notice in the 4 carbons, 1, 2, 3, 4, it ends in this C double bond O, O. We've already named the ethyl portion, so we're going to name the 4 carbons with C double bond O, O. We saw earlier that that would have been called butanoate. So ethyl butanoate. Now we're naming it as though it were an ion. In fact, it's not an ion, but it gets a name similar. So ethyl butanoate. Now if you get the name and you want to draw the molecule, start with the part that comes from the carboxylic acid, which is the second part of the name. That came from the carboxylic acid, and the first part of the name came from the alcohol. So butanoic acid, 1, 2, 3, 4, double bond O, O, and then if it were a carboxylic acid, I would write OH. But if it's an ester, instead of putting OH here, I'm going to take this portion, which came from the alcohol, and attach it. So ethyl, 2 carbons, 1, 2. So there's ethyl butanoate, right? The ethyl portion is here with 2 carbons, and the butanoate portion is here, 1, 2, 3, 4 carbons, with the sort of with something that looks like it was derived from a carboxylic acid, C double bond O with the O attached there. So there's an ester. That's one of the more complicated ones for kids to recognize and name. The last functional group that we'll look at is called an amine. We're not going to worry about amides, but we'll look at amines. An amine, as the name suggests, is derived somehow from ammonia. Ammonia, we remember, is just NH3. So ammonia has a nitrogen atom and 3 hydrogens attached. In an amine, one or more of the hydrogens is removed from the ammonia molecule, and an R group is attached instead. So there's the simplest amine. It's got a methyl group, CH3, and then it's attached to NH2. All right, so ammonia, NH3. If you remove 1 or more H's and attached methyl or alkyl groups, you get an amine. Now, the simplest amine has 1 R group attached, and the nitrogen still has 2 hydrogens. You can have 2 R groups attached to the nitrogen, and therefore only 1 hydrogen left, Or you could have all 3 hydrogens removed and 3 R groups attached. If the R groups are the same, so maybe you've taken your ammonia molecule and removed 2 hydrogens, take away a second hydrogen, and put on 2 methyl groups. So now what do we have? Well, we recognize it's an amine because of this NH in there, and then 2 identical groups. So we would call this dimethyl amine. If there was only 1 methyl group attached, CH3NH2, we would call this methyl amine. If the R groups are different, suppose one of them was methyl and one of them was ethyl, then we would name them alphabetically, ethyl methyl amine. All right, so there you have it. There's a slew of organic functional groups. We're going to take a look in the next video of a lot of examples of naming organic molecules with these different functional groups for practice, but that was intended as an overview of the different structures.